My name is Abraham Yezioro. I am glad to present the paper A Building Simplification Method for UBEM, Reduced Computation Time for Simulations on Residential Buildings in Israel. Calculating the energy consumptions of one building can take a considerable amount of time. At the urban scale, this cannot be a feasible option. This is why the UBEM is a growing field emerging from this need of evaluating large areas in a reasonable amount of time. That beyond the fact that population in urban areas are increasing and energy consumption is in the rise. The proposed tool wants to achieve the accuracy of a full simulating building, that will be the reference building, on a simplified version of it in a fraction of time and without sacrificing the accuracy of the results. Since we are proposing various simplification options, it is very important to keep consistency between them while having a high level of automation and reliability. The tool is tested and applied at two levels. One, virtual buildings, not necessarily existing one, and two, real buildings that will also serve as case studies. Both of them will be used to calibrate the tool, and the real building will be used also to validate the tool with real electricity consumption data. The task of achieving the information of the buildings, existing or new, is not always easy. It includes the building footprint, the internal layout, descriptions like apartments, cores, etc., and the properties descriptions like construction, loads, operation times, etc. Once it is achieved, modeling a full building is feasible, and this is what is called the reference building. We are proposing 5 different simplification types. The goal is to assess how they achieve the performance goal explained previously, accuracy and velocity of calculation. They go up to the maximal simplification of having one big thermal zone for the whole reference building and all the intermediate states. In order to calibrate the simplifications, a parametric model based on the reference model was created, allowing around 700 combinations per model, which are more than 4,000 for the 6 building descriptions. The parameters include here a number of floors, orientations, number of apartments per floor, and dimensions of the building. The virtual study results show that a relative error of 3% and lower is achieved for the reference, while the computation times was considerably reduced, like from 5 minutes to half a minute, which represents a very good calibration of the simplified models. The case studies chosen for this paper is a cluster of buildings which was used for testing. The junior staff dormitory is a complex of buildings in the university. The occupancy of this cluster is similar to residential buildings in the city. There is consumption measured data, which is very important for validation purposes. The results for this case study show a relative error of less than 1%, which is very good, and the computation time was reduced to 7 times faster than the reference building. In general, we get very good correlation with the measurements of all buildings in the cluster, though some gaps were found on some of them. They can be explained by changes in the use of some apartments of some of the buildings that were used as kindergartens, offices, deposits, or were just left empty. As the conclusions for the paper, we show here a very reliable tool which shows a fast simulation time with reliable results, up to 10 times faster than the simulation for a full building, and 4% or lower the error compared to the same original reference. We are recommending two of the simplification options, which show the best compromise between speed and accuracy. For the future, we want to check more parameters to perform a better calibration with reliable electricity consumption data, to implement other building types, and to implement also more and broader case studies. Thank you very much, and remember to be safe.